This is an interesting integral that I found in Feynman's book on path integrals. And in particular, the result of this integral here was used in one of my videos on path integrals, and in particular, in one of the videos that discusses the double slit experiment, which is very important in physics, in the early rise of quantum physics. But in this case, I will focus on the mathematics because I want to show that this result is correct, that this integral is equal to this expression, assuming that some quite basic conditions are satisfied, but I will not touch upon these conditions too much. It is quite obvious that they should be true. For example, the real part of this sum should be smaller than or equal to 0. And you can easily see that from here, because if, for example, these parameters are positive, well, it's quite easy to see that this integral would explode, right? Because we have exponentials that do not decay if these parameters are positive. And in particular, their sum should be less than or equal to 0. And it is quite simple to see that. It's not complicated. As well as for this, especially when you see the result, you see that we have a plus b in the denominator. So if a plus b is equal to 0, we have problems there. It's quite easy to see that. So I will not focus too much on these conditions, but I will focus on deriving this expression, because we use that, as I said, in one of my physics related contents, one of my physics related lectures. The one, the ones, more than one, I actually made two videos on the double slit experiment with the help of path integrals, and I want to show this. So let's do it. Actually, this one is quite easy to show. It's not very complicated. First, we rewrite the product of these exponentials simply as one exponential. So if we write it as one exponential, the argument of the exponential is simply the sum of these two. So we have the exponential of a of x1 minus x squared plus b x2 minus x squared. Now I will focus only on the argument, so I will just rewrite the argument, and in particular, at first, you simply expand the argument, and we want to collect the factors that multiply x squared, the factors that multiply x to the power 1, and the factors that do not multiply x, or if you want, they multiply x to the power 0. This is just algebra, so you can rewrite it as a plus b times x squared minus 2 times ax1 plus bx2 times x plus ax1 squared plus bx2 squared. Now we can focus on this first part, these first two terms, the one that contains s squared and the other one that contains x. And we can complete the square. This is something usually done in calculating integrals, and it's a very well-known technique because it's very simple. So we want to complete a square. And if we do the algebra, we can rewrite these two terms like this. So we have the square root of a plus b times x minus ax1 plus bx2 divided by the square root of a plus b, and this is squared, but in order to retrieve the previous expression, we have to add something here that does not depend on x. So when you square this expression, the first element here, the first term squared, will be this one. Then when you consider the cross, the mixed product, so you have twice this term multiplied by this. When you do that, you get this term here. And then you also have to square this, but this is a term that does not appear in the previous expression. So we have to subtract ax1 plus bx2 squared divided by a plus b. So you get back the previous expression. Then you can put together this term with these two. So I will skip the algebra, it's very simple. There is nothing mysterious about that. When you put together these terms, you get AB divided by A plus B x1 minus x2 squared. And this term, remember, that appears inside the exponential. So we have the exponential of this term squared plus this term here. You can see that this term does not contain x. So we can factor out the exponential, that exponential from the integral. Remember where we started. We started from this. So we have the integral of this from minus infinity to plus infinity. This means that we have the exponential of this term. So I can write it as x of ab divided by a plus b x1 minus x2 squared, and this multiplies the integral from minus infinity to plus infinity of the exponential of a plus b times x, and then we have minus ax1 plus bx2 divided by the square root of a plus b squared dx. Now, for convenience, we can simply rewrite this term here. We can simply call it x0 or x naught, because this will not appear in the final expression. It's like this is related to the mean value of the Gaussian distribution, so it's proportional to that. And this square root of a plus b is related to the variance of the Gaussian distribution. So let's focus only on this integral here. Then we have to remind ourselves that we have to multiply the final result by this exponential here. And you can see that indeed that exponential will appear in the final expression. So we have already obtained this part. We have to prove that the other term is this one, and that comes from integrating this Gaussian distribution here. So let's rewrite it here in the following fashion: integral from minus infinity to plus infinity of the exponential of, so here we have a plus b x, or if you want, we can also factor it out of the square if you want, but let's leave it here. So square root of a plus b x minus x0 squared. So I have rewritten the expression in this fashion. Now, when we have such a Gaussian integral, and we integrate it from minus infinity to plus infinity, the shift from the shift due to the mean value does not give any contribution to the integral. It's quite easy to show. So if you want, you can also set it to 0 if you prefer, because it will give us no contribution. It's quite easy. So, these kind of integrals are very well known. Integrals from minus infinity to plus infinity of exponential of this kind. Minus x minus some average value of the distribution that I can call x tilde, sorry, x bar if you want, squared divided by 2 sigma squared dx, where sigma squared is the variance or sigma is the standard deviation of the Gaussian distribution. One can show with very simple multivariable calculus techniques that this integral integrates to square root of 2 pi sigma squared inside this square root here. So if you want, you can factor out sigma squared and you get sigma. But anyway, you can write it like this, and therefore this mean value here gives no contribution. So if you want, you can set it to 0 very, very easily. And these two integrals have the same form. It's quite easy to see that. So if you extract this square root of a plus b from this square, you have a plus b. And of course, that a plus b represents this minus 1 over 2 sigma squared. So it's as if we can set sigma squared equal to minus 1 divided by 2 times a plus b. So the final result here would be the square root of 2 pi, and then we multiply by minus 1 over 2a plus b. So we can divide by 2, so we can simplify this factor of 2, and we finally get that this is equal to the square root of minus pi divided by a plus b, which is exactly this term here. And remember that we have to multiply by this that we have already found while doing these algebraic manipulations. You get this term, this multiplicative term that arises in the expressions, and that's basically it. So we have already shown that this equality here holds. And remember that there are some conditions, of course, to be satisfied, because the integrals that we have here must converge. So in order for the integral to converge, there are some simple formulas that must hold, some simple inequalities that must be satisfied.